Software Engineering Radio, Episode 58, Product Line Engineering, Part 2.
Hello everybody, to another episode of Software Engineering Radio. In this episode we're going to talk about product lines again. So this is the sequel to the original product lines episode. This time we're going to talk about more implementation side stuff, handling variabilities. You'll probably also note that this episode is probably the best sound quality ever. This is because Michael has invested in some really cool recording equipment, and we have some really professional mics here. And so you should notice the difference, hopefully.
Hopefully.
That's the plan. Okay, so before we start with today's kind of real core topic, do we want to very briefly revisit what we talked about in the first product lines episode? Do you want to talk about some of these things briefly?
Yeah, in the first episode, we motivated software product lines, why it is a good idea. Well, and to recap that, it's a good idea whenever you build several products, several similar products based on the same assets, based on the same components. And we also talked about problem and solution space. We talked about features, and we talked about variability in the solution space and the problem space where the variability actually stems from.
So today we're going to look a bit more closely at how you can represent and formally model variabilities, and then in the second part, how you can actually implement variable parts of a system in the implementation code.
Yeah. And in the process of software product line engineering, we are basically at the step of the domain analysis, where the key goal is first to scope your product line. What kind of features, what kind of products do you want to have in your product line? Which ones are out? You want to define a common vocabulary. Some would also call it ontology.
Taxonomy.
And the outcome would be a domain model, then further down the road, where you have all the dependencies, associations between the names, the terms that you just defined, how they relate to each other. And at the end, you would do a variability analysis of your products. You would analyze the features of your products and try to figure out where are the common parts and where do they differentiate, where's the variability between them.
So what you're saying is that there is a set of features and maybe later then implementation components that is common to all of the products in the product line, and others are optional or whatever the constraint may be.
Correct. To start off our discussion on variability, I want to come back to our separation between problem and solution space. And to model variability in the problem space, you have several options. One is a feature model that lists your features. Basically, the requirements get grouped into features. And you then structure those features hierarchically, and you note which ones are optional, which ones are alternatives, and which ones are mandatory. You describe your variability using that means, using a feature model, or in complex situation, you would then use a domain-specific language.
Right, and the difference is basically that with a feature model, what you do is you configure options from a set of predefined alternatives, whereas the feature model defines the configuration space, the available combinations of features. Okay, and so that only lets you express a certain kind of variability, which could be called configuration variability, or others call it non-structural variability. The other kind of variability is if you really want to describe a structure or a business process or something as part of your requirements in the problem space, then you can't do this with a feature model. A feature model could describe variants of a given business process, for example, but you can't creatively construct an arbitrary business process. And the way to do that is to use whatever kinds of modeling languages. Domain-specific languages, you can do it with UML activity diagrams in the case of business processes. And theoretically speaking, a feature model is just a specific kind of modeling language which allows you to express configuration options. Okay, so it's not completely different. It's just a different, expressive power that you have in your languages. So we talked about what feature models are in the last episode, so you should maybe go back and listen to that if you want to know what this is. But feature models are basically a formalism to describe configuration variability.
And we described what kind of variability you can have and how you would describe it in the problem space. Now, talking about the solution space, you have all kinds of variability mechanisms, and that is actually what we dedicated this episode for.
Right, but before we go there is something else I briefly want to talk about, and that is before we look about the specific means of implementing variabilities, talk about the different kinds of variability in the sense what things can be variable. For example, in a software system, you can either have variable structure or variable behavior. Okay, so that's two completely different kinds that need to be addressed somehow. The other thing is that you might have variability with regards to functional requirements. For example, do I have to have a billing option in my system or not? The other thing is variability with regards to non-functional requirements, such as security, failover, load balancing, scalability. So it's just different kinds of variability. There is another kind that's interesting, or another dimension that is interesting to distinguish, and that is features that can be clearly localized, modularized, and others that are more aspectual. For example,
but that you would only realize when you actually implement it, when you try to implement this variability.
Absolutely. But the nice thing about feature models is that in your feature model, let's say the problem space, this distinction is not apparent. Okay, so you can abstract over these differences. And that is one of the really big advantages of feature models compared to, for example, using some kind of UML-ish notation to describe these kinds of variable aspects of a system. And just to finish that, modularizable features are those that can be, localized in the sense that either the system has the billing component or it doesn't have it. Whereas aspectual features are a bit more tricky in the implementation because, for example, the feature security is something that might require changes in 15 different places in your resulting system. And again, as we said, the feature model doesn't show that. And that's actually a big advantage because at the time when you define what the features are and what the variability is, you don't care about these different implementation alternatives.
Okay, now looking at the solution space, we are going to discuss the various options, the various variability mechanisms that you have in the solution space.
And the solution space in this context is specifically source code. Okay, so we do not, and that's maybe an outlook to some future episode, we do not consider how, for example, you describe variabilities in models or something.
Or documentation.
Or something.
Just generally all the other core assets. The other core assets are also important, but for this episode, we focus on the source code variability.
Right. So we don't consider model-driven development and the models that are produced as part of that as something that we want to vary using variability analysis and variability modeling and stuff. That's something for maybe a future episode. So we are going to focus on source code primarily.
One of the key properties of a variability mechanism is its binding time. Binding time means when do you have to make the decision to select one variation at a certain variation point. And with variation point, we mean the location in the source code or your configuration where you decide on one of the options, one of the alternatives, or where you set a specific value to identify this variant.
And of course, each of these different alternatives, which we'll discuss shortly, has consequences with regards to performance, flexibility, file size, and so on.
And also debugging.
And debugging, yeah, right. The more you do dynamically, the harder it is. That's what you want to say, I guess.
Right.
So which typical binding times and binding techniques are there?
Well, the trivial one, or the one that we are very used to, is the let's call it source time, binding time, when you do basically cut and paste and manual programming, and when you just put in different variations in your source code manually.
So that's maybe, it's not even really a variability mechanism, right? I mean, because that's just bare bones coding something different.
Yeah. So source time binding means we really touch manually the code or let a generator generate the code at source time.
So you'll probably agree that manual changes in the source code aren't really what we'd like to call a variability mechanism, because it's just what we want to avoid. We don't want to hard code each of the different variants separately. So that's not really an alternative, right?
Right.
But it becomes an alternative if you use generators, because then the code is generated from some high-level artifacts and then you express the variability in the models.
Yes.
Okay, but we're not, again, we don't go down this route. I just want to kind of, specify where there would be the point to connect to in some other episode.
The next binding time would be compile time, where you would have function overloading, where you would have a precompiler or template evaluations in C++ and now also in Java, or for example static aspect weaving. This also happens at compile time.
Yeah, are we sure that in Java it's actually compile time with this? I thought, is it really compile time? I mean, it's not the same as templates, right? In C++ from the implementation perspective. I'm actually not really sure if this qualifies as... It's probably compile time, you're probably right. Anyway, we can cut this out. That's one of the tricks of podcasters, that they talk nonsense and then they'll say, we can cut this out, and then they'll leave it in, so people have something to laugh about.
Okay. Next one is, of course, link time. What do we do after compilation? We link it. In Java, this step is not so obvious. Here you might associate it with class loading. In C++ or other languages, it would be the loading, the association of DLLs.
Right. So the next step is deployment time or configuration time. This is especially relevant in the context of where you use, a middleware platform as your deployment target, where you have 5 million different configuration options that you can decide upon, not during programming, but rather when you deploy the component or the object or whatever the building block is that your middleware supports. Whenever you deploy this onto your container or application server, then you make some decisions. For example, how big the pool size would be for an enterprise bean or something, right?
And finally, we have runtime binding, and that means really during runtime we make decisions. In the simplest case, this is just an if statement. If I'm in that variant, then choose this option, or a factory or a strategy that we select at runtime.
Right, but there are a real, a boatload of additional mechanisms at runtime. For example, virtual function calls are polymorphism is a way of late resolving of variants. Things like using factories, for instance, for instantiating certain classes or components or objects. Delegation in general, strategy pattern. And then, of course, a little bit more advanced meta programming, where you use reflection and dynamic runtime code generation. Look at Ruby, for example, or Lisp, where you can build complete different program structures at runtime using the meta programming facilities. Let's briefly look at some of the consequences. So doing things at runtime is probably great because you can decide very late. So what's the drawback?
At runtime, you have, of course, the greatest flexibility. But as always, flexibility bites performance, or how you call it. As soon as you have something really flexible, the performance is negatively impacted. Second thing is code size. I mean, think about, for example, interceptors that you want to use during runtime, and have, for example, also a plugin infrastructure, plugins combined with interceptors. you might optimize it, but still, if you would have a code generated that does optimally exactly that, what it's supposed to do, exactly this variant only, you have the smallest code size and you have the fastest performance. And this contrasts runtime binding time with source time binding. And everything in between, well, is just like a slow degradation of flexibility.
Small increase if you start from source and go to runtime, right?
Right, and the performance is decreased. Not in every case, but generally speaking.
Yeah, and there is another aspect, I guess. For example, I think code that has all its different variants in thousands of if statements and strategy patterns. I mean, or you even using crazy meta programming stuff. What about debugging? I mean, that's also an aspect, I guess, that has to be considered.
I guess debugging is then in those cases really difficult, and having source code at the end for your product, for your single product that just contains those code lines that are actually needed and executed by that variant, then that is the simplest case and the easiest to debug.
So the question which mechanism you use for implementing a particular variability probably then depends on a trade-off between the usual aspects, performance, code size, flexibility, and you can't have all. You have to decide for one of these.
Yeah, right. So it's the non-functional properties that your products at the end require. It's the requirements basically of your products, but it's also the available mechanisms for your core asset, for your tools, for the technology. If the technology doesn't offer this kind of binding time or this kind of variability mechanism, for example, in C, you don't have reflection out of the box. So you cannot use those options.
But you have void pointers. They give you almost as much power.
Oh, great. They rule.
Yes. Actually, we should add this variability. Use void pointers for everything.
And other things are just skills and the environment and how you generally deal with your product line. Some in the software product line community even advise that choosing from a small collection of variability mechanisms is sometimes better than having a large set and allowing the developers to use a large set of variability mechanisms, because new people in the team, they will be just confused and will be giving them a hard time learning all the variability mechanisms and just making more faults. It's harder to maintain and harder to develop your variants.
Yeah, because each of these variability mechanisms in the worst case comes with its own tool. Consider a generator or an aspect weaver, right? So if you use all of them, you're just probably going to result in tool hell.
And here we put into the show notes a good reference to a paper written by Felix Bachmann of the SEI.
Okay, and that paper is about what? Just to give
It's about variability. It's about variability mechanisms, and it's a nice summary of what's available and what's the current state of research on that topic.
Okay. So we're now going to look at some of these variability mechanisms in detail, okay? And we're not going to cover generators because that's a different topic, and we're not going to cover manual changing of the source code because that's, as we said, not a real mechanism after all. So the first one we're going to look at briefly is function overloading or method overloading. I guess everybody knows that from C++, for example, you can, for example, define, or also Java, you can define, for example, a function or a method that adds two numbers, x and y, and you can define this function taking two integers as well as taking two doubles, right? And the compiler figures out which of these two overloaded functions to call. Now, just to be precise here, this is not polymorphism. Okay, it's not about resolving the dynamic type of the object at runtime and then using this kind of dynamic dispatch table to find out what the method is. Rather, the compiler knows what the data type of the two arguments is double or int, and then can statically determine what to do. So this is really something that happens at compile time, although it's, as I said, typically a little bit confused with polymorphic overloading.
The next mechanism that we want to discuss is for example, the C and C++ preprocessor with its macros. And one of a really good example where this kind of variability mechanism has been stressed a lot.
To the extreme, maybe.
Is the adaptive communication environment, short just ACE, which supports a really abundant list of operating system and compiler combinations. And to achieve this variability in a C++ framework, the development team had chosen to use ifdefs at many locations, especially at the OS abstraction layer, where all the available features of an operating system and all the funny and crazy bugs of compilers are selected, and you would have then a configuration file where you specifically configure your library to obey those features and restrictions of your platform that you're working on.
So what is an ifdef?
An ifdef is a preprocessor statement that gets evaluated before the actual compilation step, and with that you can select conditionally whether a piece of source code is considered during compilation or not.
So you say ifdef this and that feature, then you have a piece of code, and if the variable this and that feature isn't defined during compilation, this piece of code is just removed from the compilation process.
Right.
So that's kind of bare bones, brute force, source code modification based on a set of features or a set of constants or whatever.
Yes.
And of course, just to evaluate each of these mechanisms a little bit, the problem with this mechanism is that it provides absolutely no locality. So if a certain feature requires changes in 25 different places in the source code, then you have this ifdef such and such feature in 25 different locations. And
grep becomes your best friend.
Correct, yes. Yes. And also if you have certain features that are necessary only if some combination, so this becomes really, really complex because all the different variants are intermixed in one, basically in one text file, in one piece of source code. So I think you'd agree that this doesn't really scale very well.
But it was the means and the thing to use at a certain point in time when there were no generators available.
Yes, and no aspect orientation for C.
That's the only option to do it and to be really fast because you don't have any runtime impact because you cut out those code segments that are not relevant for your platform.
Yeah, but at least in C, the funny thing is that, of course, the compiler doesn't know how a piece of source code has been created. So it might happen that your ifdefs after throwing out the code that shouldn't be compiled results in code that can't be compiled because there is something wrong. So you don't have any safety net here, right? So it's just it's up to you to not confuse things there.
Yeah.
And just to relate this, there are other much more sophisticated macro systems, for example in Lisp, or in more niche languages like Converge, or as far as I know, also in a language called Template Haskell, which we don't know much about. Maybe Arno does. So the point is, such a macro or preprocessor system is actually quite powerful if it is better integrated with the type system of the host language. And that's not the case in C. It's just text processing. So that's the problem.
Another mechanism also heavily used in C++ are templates. We don't talk about template metaprogramming, but generally using templates.
We'll have a separate episode on crazy template metaprogramming, I guess.
Using templates, for example, to specify whether a certain class should be protected by a synchronization log or not, whether it should use a special memory allocator or not, or generally configuring your classes with other classes and data types.
So, and the important thing to know here is that in C++, templates are actually evaluated during compile time, in the sense that if you have a templated class that you can parameterize with some other template, for example, a very simple case, you have a collection class and you can templatize it with the element type of the collection, then what the C++ compiler does is it actually creates machine code for each of the different variants. So there is nothing going on at runtime where there is only some dynamic lookup of the parameter. It really generates two different pieces of machine code. And therefore it's very, very fast because the variability is resolved completely at runtime. At compile time. Disadvantages, of course, if you have 25 different element types for your collection, your code size increases by a factor of 25 because machine code is generated for each of the alternatives. So it's again this trade-off. It's faster, but it's bigger.
The next mechanism we want to discuss is aspect weaving, actually static aspect weaving. There's also dynamic aspect weaving, but we leave that out for the moment.
Especially since we're talking about compile time mechanism at this time.
Right. So AOP is generally a mechanism to localize cross-cutting concerns that are typically spread all over your source code that is not localized, and AOP helps you to localize those cross-cutting functionalities into a single or hopefully very few compilation units. They are then called aspects.
Right, and what you can do is, of course, if you have a certain variability that you want to inject into the existing code, you can just weave this in as an aspect. And aspect weaving, if we talk about static aspect weaving happens at compile time, or more specifically at weave time, which is basically the same as compilation. So the bytecode is actually modified, so there is no runtime overhead. Almost no runtime overhead. It depends on what kind of aspects you use. But generally, there is very little and usually none.
And before we get all the comments, we talk about as aspect J does it today.
Yes, so indeed. And it has, and also we're going to have a separate episode on all these AOP details later. We already identified 2 potential candidates today who will do this. What is interesting is that, so what can aspects introduce? So if you look at aspect J and also at aspect C++, the 2 most popular static aspect weaving tools in use today, then they can not only add advice code, which is, behavior that is executed before, after, or instead of other behavior. So you have a method, blah, 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 and you can have an aspect that says after blah, 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 do something else. And but what aspects can also do, and that is maybe even more interesting here in the context of variant management, is they can introduce additional operations or additional attributes or additional interface implementations to existing classes. And that means that you can localize the structures, members, classes, attributes, and so on, that you need for a given feature into a separate aspect and then weave in this aspect. So you have localized not only the additional behavior you want to have for a specific variant for behavior variability, but also you can have structural variability localized into an aspect and then weave in this additional class structure into the existing classes. And that is quite powerful.
One of the experiences I made applying that is that I had to prepare my plain Java source code, for example, with certain hooks that I could later use with aspects to hook in my additional functionality, my additional features.
Right. I mean, this is, one of the advantages of aspect-oriented programming, although this should probably go into this other episode, is that people say you can add all kinds of stuff after the fact. You don't have to think about things in the beginning. You can add it later. And I think this is technically true, but if you want to design or build a really well-designed aspect-oriented program, then you have to pre-think certain variabilities and hooks as in OO. So, I mean, some people use aspect orientation to patch crappy code without modifying it. That's valid use of AOP, or let's say it's a valid use of aspect J, but it's not what the AOP people anticipated or expected AOP to be like.
Just to have it mentioned, there has been some effort by IBM with the HyperJ project, where they actually envisioned to truly encapsulate features and slices of functionality, and later to basically build a full-fledged application. You would just merge those hyper slices, they called it, the features together to an application. But lately there hasn't been much news about this project.
Right. We talked about that before, but I didn't mention that because I didn't think of it. There is a new project which they call CME, the Concern Manipulation Environment, and I think that is the successor to HyperJ. But still, it's not something that many people talk about these days. So it's not really important, I guess. Okay, so now we leave compile time and we go to deployment time, which is the next kind of level of flexibility. And so, for example, if you consider you have a J2E application server and you deploy a certain EJB, then you can pass in configuration parameters to this EJB. You can define its pool size. You can say whether it should have all kinds of different security mechanisms applied to it. You can say whether it should be replicated over different instances of your application server, and so on, and so on, and so on. So this is variability that you define during configuration or deployment time. A specific way of doing that is using interceptors. And maybe, Michael, since this is a topic that's probably very near and dear to your heart from your Corba history, you want to talk about it?
Yeah, interceptors are one means to inject new or additional functionality later than at source time. You prepare an infrastructure, you build an infrastructure in your application that allows you later to inject various interceptors to fulfill certain tasks. Often those tasks are then non-functional concerns, like, for example, security or transactions or so in distributed infrastructures. One way to implement such an interceptor infrastructure is to use a factory and proxies. So the factory is asked for the proxy, and the proxy then has a set of interception hooks in it that as soon as the client accesses the proxy, it will transparently apply all the interceptors in its chain. And basically, the proxy allows you to shield the actual implementation component from the complexity of managing all those interceptors and applying the strategies that they might contain.
So, in typical hooks where you can put in behavior is, again, before and after. So if a client calls a method on the object, in fact, of course, he calls it on the proxy. That's the whole point of a proxy. Then the proxy maybe calls on the interceptors that are configured a method called before invocation and passes in the method that's called, the method name that's called, and the parameters. And then the interceptor can do something, for example, logging the method call or checking some permissions or doing whatever else. And then the proxy forwards the call to the original component. So before and after, just as an aspect orientation, are typical hooks for interceptors.
The next variability mechanisms that we want to discuss are load time mechanisms. In static languages such as C and C++, you can load different libraries, dynamically linked libraries, DLLs in the Windows world that define the same entry points. And the entry points are basically your API that is used to access the functionality contained within the library. Those entry points need to stay the same, but besides that, you can then choose various implementations, various compatible libraries that you exchange based on the kind of variation you want to achieve here. And in Java, the pendant here, the equivalent is class loading. Also, the variability mechanism, in fact, will be a runtime solution using polymorphism.
Right. So and in DLLs, what happens is that basically when a DLL is loaded, a bunch of pointers are, redirected to point to the actual entry points in the file that has been mapped into memory now. So that's why it's a link time or a load time mechanism.
And with Java class loading, you would have to have Java interfaces specified and then have just the implementations in different class files.
Strategy pattern or bridge pattern.
Right.
Okay, so that's actually the next mechanism. Let's look at runtime mechanism, polymorphism. I don't know how much we really have to talk about that, because polymorphism, I think, is something everybody knows. The idea is that if you have different subclasses that each define the same method, and you call this method, then the actual code that's executed depends on the dynamic subtype. So you have this table that dispatches the operation you call to the specific method. That's actually the distinction people make, the operation and the method that depends on that corresponds to the dynamic type.
What potential further mechanisms do languages such as Java offer us to implement variability?
Well, in Java, there isn't very much, actually. What you can do is, for example, you can dynamically call methods by using Java reflection. So based on some configuration option that maybe is just the name of a method you want to call, you can dynamically find this method and then call it by reflection. So it's not just polymorphism or something. It's really determining the name of a method that should be called by whatever means. For example, you can write the name of the method into a configuration file, read this file, and then dynamically call the method without knowing that this method exists on the class or without having it defined in some kind of interface. So you can call any method by using reflection. And of course, if the method isn't there, we get some kind of exception. So that's rather boring. You can't do very much in Java. However, in somewhat more sophisticated OO languages, you have much more extensive ways of metaprogramming. For example, you can change the meaning of certain trivial or built-in operations. For example, if you call a method in CLOS, which is the Common Lisp Object System, then you can change the interpreter in a way so that calling a method means something different. For example, first do some log output and then invoke the actual method. It's kind of aspect orientation. And if people know this kind of meta-object protocol stuff that has been implemented in CLOS is actually the precursor to aspect orientation. In other languages such as Smalltalk or Self or Ruby, you have similar ways of doing this kind of meta-programming. There are for example, in Ruby, and we talk about that in the episode on Ruby DSLs. So when a Ruby class is loaded, or when the compiler reads the definition, the code that defines a Ruby class, then the interpreter actually interprets this definition. And as part of this interpretation, as part of the class definition, you can execute other methods, which in turn change this definition. So you can basically have self-modifying code. So you can have a class definition that as part of its own definition calls a method called add the following attributes, name, first name, last name. And what this method does is it dynamically adds the attributes, name, first name, and last name, to the class that's currently defined. Now, this sounds like something that you can, use to shoot you into your own foot.
That is what I wanted to say. As somebody who's rather conservative on this edge, I would have asked, how could I misuse that, and how could I actually later then know what's going on? How could I debug such a system?
I have to reply that, but so you're kind of saying these dynamic languages with all this meta programming stuff, it's too complex and you can misuse it. I just want to say, you can do the same, maybe even worse things in static languages. Look at this C++ template meta programming stuff. Isn't that a misuse in a static language?
But I have a harder time doing it not right.
Okay. Yeah, this is a very powerful mechanism. You can do all kinds of crazy things. On the other side, it is extremely powerful, and all the features that people talk about Ruby, the hype around Ruby is this metaprogramming stuff. Ruby on Rails is implemented based on this stuff completely.
but it's shielded by a simple programming interface, by a simple DSL, basically.
Absolutely. I'm not saying that you have to expose all these things. That's probably true for all those mechanisms. You want to provide a nice way of configuring them, of using them. You can do this using models. You can do this using internal DSLs in Ruby. You can do it using macros in CLOS. So that's clear. You can also hide it behind normal classes in C++. The Boost library, for example, uses template meta programming to the extreme internally, but you as the user of the library, you don't see this. So that's all right. The same is true for Ruby. You don't want to expose this to the framework user, but that's probably true for most variabilities. You want to still use the mechanism.
Okay, here I agree.
Okay.
Okay, I think we just discussed a nice set of variability mechanisms. Something that I want to mention here also is that in some cases it might be useful to use combinations of those variability mechanisms. For example, use some configuration files, maybe even format them using some XML style. Here, XML makes really sense for configuration files. And then read out this configuration where you declaratively state your configuration and use some runtime or load time mechanism to then configure and customize your product.
I would like to extend this thought even a little bit further. So what you say is that what you should do is you should capture the variabilities in some kind of configuration file. I use a different name. I'd say you build a model of this configuration. No, really. I mean, that's what happens. And then you can, once you have this model that clearly captures these configuration options, you can decide whether you build an interpreter of that model, which reads these options at runtime and changes stuff at runtime, or whether you build a generator, which reads these things during code generation or source time, more or less, and then generates different code. So the essence of variability management, maybe, is to formally capture the variabilities, the valid options, and the concrete selections you make for a specific product in your product line. And then you have all the different ways of implementing that. But the precondition is capturing that nicely.
Yeah. Here I really like to state something I read in the paper by Felix Bachmann. It's basically the goal of variability in software product lines is to maximize return of investment. And here it goes on, yada yada. But the key is basically that you have two cost factors. One is to build in the variability, and one is to exercise the variability.
So why is it a cost factor to use the variability? Isn't that the benefit of reusing things that you've put in before?
Yes, but it can be a benefit. In the case of generators, for example, you have a really large cost to build in the variability, to build a generator, to build the meta model, etc., to learn about the generator, and it's very easy. It's so cheap to exercise the variability. With other mechanisms, the build-in variability is quite easy. For example, with the strategy. But to implement then the various strategies, the concrete ones, basically to exercise the variability, you have a higher cost. And when you here have very many options, very many strategies, then this cost of exercising this variability explodes. And so what you should be looking for, what the message is, think about both costs. Think about how much it costs to build in this variability and to exercise it, and the combination of both, try to optimize that for the use case, for the kind of variability you have at this variation point.
So that's again where economies of scale come in. If you use the variability in different ways really, really, really often, then the cost you have to invest initially to build it, for example, this generator, doesn't really count, because you save a lot of cost when you reuse it and exercise it over and over again. If this ratio is not that, big, if you only use it, fewer times, then you might not want to take the initial investment.
So what is this fewer, for example, in the case of the generators that you are familiar with?
You mean the ratio and
The ratio?
when it starts to make sense? I mean, this is a really tough question because it depends on how much effort it is to build a generator. And that really depends on the specific kind of variability you have. I mean, you said before building a generator is very, 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 very much effort. I certainly wouldn't subscribe to that. It's more effort than just using a strategy pattern.
It's not such a big effort for Markus, but for everybody else.
No, it's just for people who are used to using the tools. It's not a big effort. So you have to add into this equation the effort that it takes to get to learn the tools with which you can do it. Same is true, if you ask Adrian Collier or Gregor Kisales, they will say, no problem with Aspect J, just do this weird point cut and some advice here and there and some introduction and that's done. But if you don't know Aspect J, getting to the point where this is easy is quite a lot of work. Same for generators. Right, so this is another dimension. How many additional tools do you have to learn? In case of, for example, the strategy pattern, you don't have to learn new tools. You just have to read the Gov book and understand it. In case of C++ templates, same thing. You don't have to use another tool. You just have to understand weird C++ template meta programming. So the effort of getting to the point where using the variability mechanism is feasible is another pre-investment.
Okay, I agree with that. So where does this leave us? Tough discussion. Now, you can, of course, associate with all the variability mechanisms the binding time. We hinted already somewhat at it, which variability mechanism is suited for what kind of binding time or requires a certain binding time. There is some variation in it. But the outline we gave should be sufficient.
Right. So I think this more or less concludes this episode. Do we have something else where we disagree upon so we can...
we leave that for the next episode.
Yeah, because when starting this episode, we actually started in a somewhat different fashion, and we noticed that we didn't agree on what we wanted to say. So we said, okay, forget about that. Postpone this to some later episode where we'll talk about these more esoteric things, and hopefully we can agree on what we want to talk about beforehand.
Okay, so stay tuned for more discussions on software product lines.
And thanks for listening. Bye.
Thanks for listening to Software Engineering Radio. If you want to get more information about Software Engineering Radio, or if you want to give us feedback, please go to our website at se-radio.net. You can also contact the team at team@se-radio.net, although we prefer entries in our comments system on the website so other people can see what you think. Software Engineering Radio wants to thank Henning Pauli for the intro and outro music, as well as Libsyn for providing the bandwidth. This episode of SE Radio, as well as all other episodes, is licensed under Creative Commons license. See the Software Engineering Radio website for details.